Okay, so welcome to our last lesson for this week. This lesson is sort of going to put everything that we've been learning about together. So let's just do a quick recap. So what do we know? Well, we know that light seems to be a wave, right? Because it shows an interference pattern when it goes through a double slit. And anything that has an interference pattern is a wave. Also, Maxwell showed it's an electromagnetic wave. But then it also seems to act like a particle, or its energies seem to come in chunks, like individual particles. And so now all of a sudden we're saying light's a particle again. So which is it? I find that textbooks seem to, well, grade 12 textbooks anyways, seem to say, well, if you're looking at light such as the photoelectric effect, it seems to be a particle, or it acts like a particle. And if you're looking at light in a different experiment, like the double slit experiment, it seems to be a wave, and it acts like a wave. But today we're going to approach the problem differently, right? It's not one or the other depending on which experiment you're doing. And so we're going to look at it from polarized light. So I'm going to teach you what polarized light is, and then we're going to do a couple experiments. Usually I do a couple experiments in class, but I found some online simulations that we're going to go through together. So this is the best we're going to be able to do. And if you have questions, be sure to ask. I'm also going to be posting a video from the Perimeter Institute. I found it on YouTube. I have the DVD, but you can't watch that. I found it on YouTube in 3 parts. So I'll post those 3 parts. So please watch that as well. They look at particle and wave duality from a different point of view, not from polarized light, but from a different point of view. So it'll be good to get the 2 different perspectives. So let's start with polarized light. What is polarized light? Well, change size. So light is electromagnetic waves. So let's look at it like that. So if we have light, it's going to have an electric portion. So let's say here we have an electric wave vibrating in this plane. It's also going to have a magnetic wave always vibrating perpendicular to that. I can't draw 3D, but you'd have a magnetic wave going perpendicular to this one. Now, unpolarized light is the electric field. Let's just focus on the electric field, not on the magnetic field. The magnetic field will always be perpendicular to the electric field. So let's just focus on one of them. The electric field is going to be vibrating in, well, all different directions. It's going to go up, out, around. It'll always have a corresponding magnetic field perpendicular to it, but it's going to just be all over the place. Okay, kind of like right here. Now, if we can sort of isolate just one direction or one plane, like this one that goes vertically, or another one that maybe goes horizontally, and that is called polarized light. And there are different ways to achieve polarized light. This is the most common wave. This is a polarizing filter. So when you send polarized light through a polarizing filter, what it does is sort of cancel out the electric fields, or dampen the electric fields until they reach 0 amplitude or 0 intensity, except for in one direction. Okay, so you can see this one, we have a vertical polarizer, and coming out of it we get vertically polarized light waves. Now in reality, what a vertical polarizer does is it cancels out all of the vertically polarized electric fields. So pretty much all of the pictures you see online are wrong. But for simplicity, let's just look at the fact that, okay, a polarizing filter, if it's vertical, we just get vertical coming through. Could be vertical magnetic fields, in which case it would be fine. Okay, so that is polarization. There are other ways to polarize it other than a polarizing filter. There's double refraction. So for example, this is a piece of calcite. Well, it's an image of a piece of calcite, and underneath you just write the word calcite, and when you put it over top, it looks like there's 2 images. Why? Well, light is getting refracted, so it's being bent, but it's getting refracted twice. Now you're not producing energy here. What's happening is half the energy is going into one, half the energy is going to the other. So for example, one is polarized horizontally and the other is polarized vertically. Okay. Reflection is also another way things polarize. If something reflects off a surface, it becomes polarized, and also scattering in the atmosphere can cause polarization. Okay, which is why we put polarizing filters on cameras, right? If you want to take a picture of, say, the ocean, but you don't want all of that glare coming off the ocean, well, that glare that's reflecting off the ocean is polarized light. So what you can do is, let's just go back. Let's say it's vertically polarized. Well, you put a polarizer that's horizontal, and none of that light will go through it. Okay, and we'll get more into that later. But also glasses. A lot of sunglasses, they say they're polarized, right? Again, it's just a way to cancel out a lot of the different vibrations that light is undergoing. Now, polarization can occur in any direction, but in order to choose a coordinate system that's nice, we like to say that light can be polarized horizontally, vertically, or at plus or minus 45 degrees. Now, because light can be polarized, we know light is a transverse wave, because longitudinal waves cannot be polarized. So light is definitely a transverse wave. If you remember from grade 11, like this is transverse, whereas longitudinal had those areas of compression and rarefaction. Okay, so light's definitely a transverse wave. So this is what we've talked about. And we've talked about the double slit experiment, showing light's a wave, and the photoelectric effect, showing light is a particle. Well, we need to settle this solution right now, because this is a debate that's been going on for hundreds of years. And every time we think we solved it, we don't. So let's look more closely at what a wave and a particle actually is. Okay, a wave, we say it's delocalized, and a particle, we say it's localized. What does that mean? Well, let's say I were to draw a particle. Here's a particle. There, particle. Now I were to say to point at that particle. Well, everyone's going to point right at that particle. Okay. Well, let's say I were to draw a wave. And I were to say to point at that wave. Would everyone point here? Or would some people point here? Would others point there? And some others point here, or here, or here, or here, or here? It's in a whole bunch of places. So it's like it's everywhere at once. So this is very, very well defined, and this is not very well defined. Localized, delocalized. Just at one place, everywhere at once. Okay, so that's the difference between waves and particles. So now, let me introduce quantum mechanics a little differently from the history lesson we did with Max Planck and Einstein. Here are the two rules. Well, there's lots of rules for quantum mechanics, but the two overall most important rules of quantum mechanics. One, the superposition principle. What does that mean? Well, it means something can be here or there, right? Just like a particle. A particle can be here or there. But the superposition principle in quantum physics says it's here and there. Okay, well, what does that sound like? It doesn't really sound like a particle, does it? You can't really say, oh, the particle's here and here. But I can say that for a wave, can't I? Particle's here and here. Not the particle, sorry, the wave is here and here. It's also here and here. Okay, and this is sort of, you probably heard the Schrodinger's cat experiment where the cat is both dead and alive. In fact, Schrodinger came up with that thought experiment because he thought this superposition principle was absolutely ridiculous. And he's like, this is so ridiculous. He says, let me prove it to you. Let's say you take a cat, put the cat in a box. Okay, inside the box you have a vial of poison. Okay, and there's a mechanism that will break that vial of poison. Now that mechanism is triggered by a radioactive particle that decays. And we can't predict when a radioactive particle decays. If you remember half-life, Half-life is a great way of figuring out how much time it will take half the number of particles decay. But to pick one particle and say at what time will that particle decay, we can't do that. It's completely random. Okay, we can say probabilities. We can say, okay, after this amount of time, there's a 50% chance that particle will decay. Okay, so close the box, and after some time, there's a 50% chance that particle is decayed, which means there's a 50% chance that violet poison has been broken, which means there's a 50% chance that cat is dead. Vice versa, there's a 50% chance the particle didn't decay, and the vial is not broken, and the cat's alive. So there's two possible states here, alive and dead. And since the odds are 50-50, well, it doesn't have to be 50-50. It could be 99% and 1%. The fact is, it's both dead and alive at the same time. So where does rule number 2 come in? This is the measurement principle. The measurement principle in quantum mechanics says rule 1 always works as long as you don't look. As long as you don't observe or make any kind of measurement whatsoever. If you do measure it, you disturb the system and you force it to choose to be one or the other. And so the cat is now dead or alive, meaning if you open the box and look, and let's say you open the box and look, well, now the cat's definitely alive. It's right there. It's okay. And you never actually did this experiment, though. This is just a thought experiment. Okay, but these are the two fundamental rules of quantum physics. Okay, not relating to cats, that's just an idea, but relating to particles. For example, an electron can be, and we'll get to this later, can be here and here at the same time. But if you try to look to see where it is, you'll only ever see it in one place. It's sort of weird. If you think about it, think about that deeply. It's like you're trying to do an experiment, but just the act of looking at the experiment changes the results of the experiment. We'll talk more about that later. Same with the video that I'm posting. It goes over more of that. And this is wave-particle duality. Why? Superposition seems like it's a wave property because it's here and here and here and here. Whereas measurement principle seems like a particle property. It's there. Okay, and so we call this wave-particle duality. Let's go back to polarizers. I want to talk a bit more about polarizers. Let's say we're going to do a couple experiments here, simulations. Let's say we have unpolarized light and it's shown at a vertical polarizing filter. Through the filter you get, well, how much of the light? All of it? Half of it? A quarter of it? Nothing? Well, in this case, you're going to get half the light. Okay? All the vertically polarized light and anything that's partially vertical and partially horizontal, like light that's at 45 degrees, you'll get the vertical component. So out of all of that light, you get half. Hold on. Okay. So that's our first question. But now we're going to extend this a little bit. This isn't Schrodinger's cat, by the way. This is Franchino's dog. I don't do experiments on him, just so you know. Number 2, unpolarized light is shown at a polarizing filter. Okay. The light that gets through then meets another filter oriented the same way. So in this diagram, I have 2 filters, both vertically polarized. What do you think is going to come out the second filter? Any ideas? Let's look at the simulation here. All right, does everybody see this? So here we have unpolarized light, and it goes through a vertical filter, so everything is vertically polarized. And when it goes through a second vertically polarized filter, everything that comes out is again vertically polarized. It's like a gate with a question. Over here, the question is, are you vertically polarized? If the answer is yes, you may pass. If the answer is no, you may not pass. So over here, all the light's vertically polarized, and it comes up to another filter with the same question. Are you vertically polarized? If the answer is yes, you may pass. In this case, all the light answers yes, yes, yes. We're all vertically polarized. So that means, let's go back to our PowerPoint. There we go. That means it's still half the light that gets through. All right, next question. We have an unpolarized light is shown at a polarizing filter at 0 degrees, and then another at 90 degrees. Through both filters, what do you get? Think about it for a second, and we'll go to the simulation and test it. How much light do you get through? Nothing. You don't get anything through. And if you have polarizing glasses at home, you can test this. You can hold one pair of glasses. You need 2 pairs of glasses. You could do it with one if you break it in half, but please don't do that. Okay, just hold one pair of glasses horizontally, look at some light, and then take the other pair and hold it vertically and look at the light. And you'll see that no light gets through. If light gets through, they're not really polarized. That's called false advertising. Right? But I mean, if you're in a store, that's an easy way to check to see if glasses really are polarized. Okay, let's go back. All right, next. Unpolarizing light is shown at a polarizing filter at 0 degrees. We'll say 0 degrees is our horizontal filter. And then another at 45 degrees. How much light gets through? All right, so think about that. We'll go back to the simulation. I can't change the orientation of the first one. It doesn't matter. We'll just put the second one at 45 degrees. It'll be the same result. Okay. This simulation isn't the greatest because it doesn't show you intensity. It just shows you the light. But if you have half the light going through the first one and then right at 45 degrees, right, you'll get, well, half the light again. Does that make sense? Half and a half. So at the very end, you end up with a quarter of the light. Let's go back. Right? So you get a quarter of the light. 1/2 times 1/2. But this is weird because if you were to draw this triangle and you were to try to calculate the components, right, you'd realize the cos of 45 degrees is not a half. It's 0.707. But the cos squared of 45 degrees is a half. And in physics, in this case, in many cases, we say the intensity of the wave is proportional to its amplitude squared. Okay, and that's a very, very important point. I have it bolded on that PowerPoint. Okay, so the amplitude squared is the intensity. Okay, amplitude and intensity are not the same thing. All right. And this is known as Malice's law for polarizers anyways. Okay, where if you have here we have a certain polarized, vertically polarized light. Okay, it's coming in to a polarizer at some angle theta to the vertical axis. And the amount coming out then would equal the amount going in times the cos squared of that angle. All right. I'll come back to that. So let's look at this. This is a chart, and if we have, let's say 0. So we have horizontally polarized light, and let's say we're going to measure an angle from 0. So this first one here, let me see if I can actually write on here. Hold on, I might have made a mistake in my recording. Did I miss something? Okay, hold on. I've just been having technical issues. I don't think I can write right on the PowerPoint. Okay, I'm just going to do this like this. All right, I think this is recording again. So let me go through this again because I wasn't recording before. So let's say we have a polarizer that's horizontally polarized, and we'll say that's at 0 degrees. And then we have a second polarizer at 0 degrees. Okay, well, how much is going in compared to how much is coming out? What is that ratio of the intensity? Well, everything is coming out compared to going in, so 1. Right? And you could test that by doing the cos squared of 0. Well, in that case, the cos of 0 is just 1, and square that is 1. So the probability of a photon, and what we're going to do is we're looking at, let's pretend it's just one photon that's horizontally polarized, and if you put it up to another horizontally polarized, it's either going to get absorbed or go through. What's the probability of each? Well, in this case, it's definitely going through, and it's not going to be absorbed. But if that second polarizer is at 45 degrees, well, if this was a beam of photons, the intensity ratio would be 1/2. Right? Close to 45 is 1 over root 2, square that, a half. But if it's a single photon, what's the probability of going through? The probability of going through is 1/2. And I'm not going to write probabilities as percentages. It's just a value between 0 and 1. Well, 1/2 would be 50%. And therefore, the probability of being absorbed by that polarizer and not going through would also be 50%. And you can continue. I'm not going to write all of this, but I will post my answers so you can see. But certainly try it yourself. This chart is on the back of your handout. For example, minus 45 degrees would be the same probabilities. Minus 30, you would have, well, 3/4. And so the probability of that one photon going through is 75%, and therefore, since probabilities must add up to 1, the probability of being absorbed is 25%. All right, so let's get back. I'm going to get out of the drawing phase. Okay, I think we're back. Let's go to the next slide. All right, so let's talk about exclusive states. So superposition really is a relative concept. It's relative concepts because it's in relation to exclusive states. Now, I've kind of mentioned exclusive states before. You might not remember the term though, but let's think back to projectile motion. I've said so many times in projectile motion, whatever happens in X has no effect to what happens in Y. Okay, X and Y are completely independent of each other. And so we say X and Y are mutually exclusive or exclusive states. Okay, another example would be here or there. What does this mean? Well, if you're here, you're definitely not there. And if you're there, you're definitely not here. Okay, so these are exclusive states. And we can use superposition with exclusive states. Now we also need to figure out, well, what are we going to measure things by? So let's say we had a photon of light coming towards us, and we wanted to make a measurement on it. Now it's polarized, but we want to know, how is it polarized? Well, we need to choose how to measure it. Are we going to take a polarizer and measure it in a horizontal or vertical? Because a photon that is horizontally polarized is definitely not vertically polarized. And if it's vertically polarized, it's definitely not horizontally polarized. So horizontal and vertical states for polarizations are mutually exclusive states. Or we can choose plus or minus 45 degrees, right? Those are also mutually exclusive states. Think of it in terms of components. If I were to write, say, a vertical and a horizontal, I cannot write this horizontal in terms of the vertical, right? Similarly, if I had a plus 45 and minus 45, I can't write one in terms of the other. These are all perpendicular. Okay, this is perpendicular to that, that's perpendicular to that. If you wanted to, you could choose plus 89 degrees and minus 1 degree. Sure, you can choose that as your measurement basis too, because they are also mutually exclusive. That's just confusing. I don't know why you choose 89 and minus 1. Usually we choose horizontal or vertical or plus or minus 45 degrees. Okay, so let's say we chose our measurement to be horizontal and vertical. So we use the HV basis. Now let's say that photon that was coming towards us was plus 45 degrees. Well, It might go through the polarizer, it might not, right? So when it comes to that polarizing filter, now let's say we make it polarizing filter horizontal when we make our measurement. We're asking a question. Our question is very simple to the photon. Are you horizontally polarized or are you vertically polarized? What do you think it's going to say? It's going to be like, am I horizontal or am I vertical? I'm both. Right? And it is both because we can write this in components. Right? We can write it has a horizontal component of 1 over root 2 plus a vertical component of 1 over root 2. Don't worry too much about the 1 over root 2. That's just your cos theta. Okay? And remember, this would be your amplitude. So the square of that is your probabilities. Okay, so the probability of it being horizontal is 50. The probability of it being vertical is 50. Okay, so now it is in a state of superposition. This, because of the measurement basis we chose, we've placed that photon in a state of superposition where it is both horizontal and vertical. Okay, so this is a wave property, right? Remember, it's both. Well, now we make the measurement. Now, when we make the measurement, it's either that one photon is either going to go through the polarizer or it's not going to go through the polarizer. If it goes through the polarizers, it's 100% horizontally polarized. Or like the cat, it's alive. It's no longer a superposition. You just use number 2. Rule number 2. Rule number 1 works unless you make a measurement, unless you look at it. The instant you look at it, you collapse the system and it's vertically polarized. Okay, so this is the idea behind superposition, and this is the idea behind measurement disturbance, and the idea behind what we call wave-particle duality. So is light a wave or a particle? Well, that's simple. Light's a wave unless you look at it, in which case it's a particle. Okay, and the double slit experiment is really, really cool because if you go into the double slit experiment even more, and you'll see this in the video I post, but if you want to know what's going through those two slits, are they waves that are diffracting or are they particles that are shooting in all different directions? The instant you look, and physicists have done that, they place detectors on the other side of the slit to see what's coming through. And you know what they detected? They detected particles flying everywhere. But you know what happened? The interference pattern on the screen disappeared. And you just had 2 bright lines, which you would expect from particles. It's weird, right? It gets even weirder than that, but let's just pause for now and continue with this. So here's another cool idea to help with understanding superposition. Now we've already said if you have, say, horizontal light going through a vertical polarizer, will it go through? No. Similarly, if you have light at plus 45 degrees and it goes through a polarizer at minus 45 degrees, will it go through? No. Okay. Well, let's say you have this plus 45 degrees polarizer, and you have this minus 45 degrees polarizer, and then in between it you place a vertical polarizer. Will light get through? Think about it. And then we're going to go to the simulation. While you're thinking, I'm going to go to the simulation. Okay. All right, so here I have the simulation. I have a vertically polarizer. I just placed a second one, but hold on, I can get rid of that. Okay, and a horizontal polarizer. Nothing gets through. Slightly different from the one on my PowerPoint, but same idea. I'm just choosing a different basis. And then the second one, I'm going to change it to be at 45 degrees. will light get through? Yes, it does. It's a little strange, isn't it? How? How does it get through? Well, let's look at each gate and the questions that are being asked. Let's go back to the PowerPoint. So here we have unpolarized light coming to the first PowerPoint. Not to the first PowerPoint, to the first polarizer. Okay, and the polarizing filter says, are you plus or minus 45 degrees? If you're plus 45, great, you make it through. All right, now the second filter is a vertical filter, and it asks that 45-degree polarized light, are you vertical or horizontal? And it's like, both, right? Because you can write that as a superposition of both. Okay, well, the part of you that's vertical, that can come through. Okay. Now we have vertical light. It goes through a negative 45-degree polarizer, and it says, are you negative 45 degrees or positive 45 degrees? And the vertical light is like, both. Right? Superposition. Like, oh, okay. Well, once you come through, I'm going to make a measurement. Boom. You are minus 45 degrees. There you go. That's how it works. Combination of superposition and measurement disturbance. Wave-particle duality. Okay, so this is the heart of quantum mechanics. Wave-particle duality is the heart of quantum mechanics. Superposition principle, measurement disturbances, right? The fact that you can have an electron acting like a wave, right? But when you go to take a measurement of it, it's now a particle, right? And all quantum objects work the same way, not just light. Wave-particle duality. This is a side note, but 3D movies, they're cool. So you wear glasses, okay? What do these glasses do? They're not the same glasses as many, many years ago where you have like red and, was it green or blue or something? And you had different colors, red light and green light, right? That's cool, that's 3D. You have red light and green light. The red light can pass through this filter, but not through that one. The green light through this filter, but not through that one, right? Bad thing is you can only have two colors. We tend to like to watch movies with more than two colors though. So this is how it works. You have two cameras. Each camera videotapes the movie from a slightly different angle. Makes sense. Everything you look at from a slightly different angle. From here and from here. Right? Two eyes are required to have depth perception. If you could only see from one eye, you wouldn't have depth perception. Right? You might try to guess based on the size of things. So if you see a car this small, you can probably guess it's probably pretty far away. Okay? But really, you don't have depth perception with only one eye. So same thing, we have two cameras. And then what those cameras do is you can project it, but one will project horizontally polarized light and the other vertical. And then your glasses are horizontally polarized and vertically polarized. One lets light through from one camera, one lets light through from the other camera. And it sort of gives you the idea of 3D. That's a little more complicated because in between those polarizers, they have circular polarizers. And this is important because if you were to watch a movie and do this, if you didn't have those circular polarizers, the whole screen would go black. Or it would switch and it would just get very confusing. Okay, so to avoid that, we have it circularly polarized. All right, so I want to go back to that photon. So the chart that we were doing before, this is very similar. So we have a single photon, it has a polarization, and we're going to make a measurement. We're going to do it in the HV basis, horizontal vertical basis. And I put up one example here. I recommend you try the rest, but I'll put up my answers for all of them. So in your horizontal component, you will have 1 over root 2. Okay, this is the amplitude. Okay, so your vertical component is just cos theta, is also 1 over root 2. Okay, so your photon's at 45 degrees. No, sorry, your polarizing filter is at 45 degrees. Right? And your photon is horizontally polarized. Well, once it goes through that polarizing filter, it's both horizontally and vertically polarized. Okay, we write it like this. So actually, we write it, you may have seen this before, you may not, but we write it like this. Okay, the 45-degree state, this is called ket notation. Okay, these brackets are ket notation, and it just says, all it means is that what's inside these brackets is a state. Right? We use this a lot in quantum mechanics. You may have seen this, I don't know if you use those in chemistry, when you do spin, that's an up spin, down spin, you put it inside of these brackets to show what state it's in. Okay, would equal 1 over root 2 of your vertical state plus 1 over root 2 of your horizontal state. Okay, and these are your amplitudes. But if you want to know the probability that it's going to be horizontal, you square your amplitude. Remember, I bolded that, said it's very, very important. Right? Your probability is the square of your amplitude. Okay, so the probability that it's vertical is 1 over root 2 squared, which is 1/2, so 50%. Right? The probability that it's horizontal, again, 50%. All right. Now this is sort of different from a classical wave. This I have to mention because a lot of people, when they think of wave, they go back to grade 11, like, slinky. It's like, no. Here's the difference. When you look at a slinky, right, you can look at a slinky and you can say, oh, the slinky exists here. Oh, hold on. The slinky exists here, it exists here, it exists here, it exists here, it exists here. So what are you doing? You're saying the slinky has a position, right? And so you associate waves, whether it's a slinky or maybe a wave at an ocean, any type of wave you can think of, a wave at a sports event, right? You're looking at that wave existing in those places. You're looking at it a wave of position. A quantum wave is not a wave of position, right? So when you look at, say, the wave that is formed from an electron around an atom, that is not a wave of position. You cannot say the electron is like waving around an atom. No, it's not doing that. In quantum mechanics, right, the wave is a wave of probability, not a wave of position, not a wave of displacement. Okay, a wave of probability. Okay, for example, with photon polarization, we don't have an infinite number of states. You have two mutually exclusive states. And what did we do? We took a square of the amplitude and we got a probability for a given state. We didn't get its position, we got its probability. Okay, and this equation here, you don't have to know this, but this shows the wave function of any quantum object. This is called Schrodinger's equation. It's a very famous equation. When you start studying, or if you continue on into physics and you do quantum mechanics, you will. This is the F equals ma of quantum mechanics. Okay, and it basically says the probability of finding certain quantum objects in certain states. Okay, it's a wave function, but it's a wave of probability. I've said that like 17 times. Okay, no questions? Any? I don't hear any questions, so I guess everybody was good with that. If not, send me some questions. We will continue into quantum physics next week. I would like to say things won't get weirder, but they just keep getting weirder, so enjoy. Lots of fun. Have a good long week.